Okay. So we start? Yeah, Zafira-san, can you start first?
Hello? Can you hear me?
I cannot hear your voice.
Hello? Hello?
Okay.
Okay. So I try to compare the result. So this one, we want to compare the degree of coupling. So this formula based on this is we calculate from base capacity design, and this is from Tmax from the Stera 3D. And then this is it's have a little bit different. And I also compare with a smaller beam. It's almost the same. So for the steel beam, it might be different because when we run into the Stera 3D, not, for example, we design for 2,900, not every coupling beam have shear 2,900 when we push over the model. So this is from the data beam. So I think
How much T in case of max beam?
max beam in this 750. So in 750, max beam is this one. So shear is, excuse me, maximum at the bottom, level 1 is 700 and the top story is 300. And then I try to compare with smaller beam. So this one 300 by 100 steel beam. So we can see like almost the beam reached its maximum around 200 kilonewton. But if we design the beam with 750, means not every beam have 200 reach the maximum capacity. And the ductility also small. And if we compare to the smaller beam, the ductility is quite big, it's like 5.
So this is a small beam.
Yes, this is 300 times 100.
Okay. And
So
the shear capacity is almost 200.
yes, the maximum capacity. And then this one is 700 times 350.
Okay. So some beam doesn't reach
Maximum.
maximum. This is the reason T is small. Could you go back to the first?
This one?
Yeah.
Yep.
Okay. So TL is smaller than upper one.
Yes. But this is we calculate manually. So this is the capacity times the 800, the length of between two walls.
Okay.
This is total height.
Could you
And
click, I mean, this one also use the same formula?
this one, same formula, but this is come from Stera 3D. The shear force come from Stera 3D.
So upper one, you assume all floor, all beam has the same capacity,
Yes,
2,900.
yes,
But lower case, T value is different.
yes,
You know the story.
yes.
And what is the 2,900? How did you
It's the capacity of the steel beam, Sensei,
beam?
from the
Go
data
back
beam,
to the large size beam, max beam data.
max beam data. So this
Our Excel file you explained.
one.
Okay, this
This
one.
one, yes.
So this reach ductility over 1,
Yes.
and the capacity is almost 745.
Yes.
But in the previous,
In here,
this is not the 755,
This-
2,100.
this one is from the max beam sensei. Like when, for example, from here, so that far beam. So we check from here. This one. So from MY 3500 times 1.3 divided by 2.
So it means both end of the steel beam is yielding, and My is this value.
Yes.
So what is how did you calculate 750? The other case.
The other case is from after we push over,
Hmm.
we get from the max beam from here.
Yeah, but the situation is the same. Both end is yielding, and the shear force, so both end is My,
Yes.
and the shear force is 750. But in your calculation, 2,000 something, right?
Yeah.
So why the value is different?
356. From MY, we can get QY, right, Sensei? We can
Now, could
transfer
you show me the max beam? Max beam
max beam.
data? And
This one.
optimize it. Okay, so yield force is it is not the same as
This is ME. The one here is Q.
yeah. This is
So this- yeah.
almost 797,
Mm.
and the moment at that time is 0.157 multiply 6.
About
Oh,
6.
okay.
Mhm.
So this is My.
Yes.
But the previous, data you showed me, My is not this value.
Yeah, this one.
Why MI is different?
This is result after for pushover, but this is my understanding data beam is this is the capacity, the maximum capacity of the beam.
But
So-
after making pushover,
Mm.
yielding happens at the beam end,
Yes.
and MI is this value.
Yes.
So it must be the capacity.
But it's not the maximum. I mean, it doesn't reach the maximum.
But the
If-
ductility factor is 1.
Okay,
More than-
let me compare about this one. So data beam is this one. So it's about 29,000
Yeah.
kilonewton centimeter. And then we open max beam.
Mm.
So yeah, it's same here. Right. 2,000.
Okay.
Yeah.
And
For
the
this,
factor is almost 5.
yes. This is for smaller beam.
Mhm.
Yeah.
The small beam is okay. It's
Yeah.
consistent.
But for the bigger beam, 700 times 350, it's a bit different. So this is the maximum,
Okay.
and this is we get from 1/250 pushover.
Mm. So if you push more, this moment will increase.
Might be.
might be.
We can try it.
Mhm.
For example, 1/50.
Mm. Oh, no. You must click this one. Static.
Or static.
Mm. You want to do pushover, right?
Yes. So this one, 335,000.
Yeah.
This is
But still
this
small.
one small.
Mm.
And the activity is 1.
Mm. Could you go back to Stella 3D?
Okay.
And could you click this one?
This one.
Mm-mm. And could you click this one?
Okay.
Yeah, and this one.
So
Yeah, and could you do pushover?
1/50.
Yeah, okay, static.
Static.
And could you select the member response from here?
Member response from here.
No, this one. Yeah. And start. Oh, it's not reaching the maximum. So this is, okay, so 0.6, almost 0.6. So if it's 1.0, this will be 3, not click, 0.335. I mean, but now it is 0.2.
Yes.
Almost 60% of the capacity. So even the activity factor is more than 1, the
Mhm.
beam is not yielding yet. No, this is a reason. Okay. Okay, I understand. Okay.
Okay.
Yeah. Mm.
And then, so can we consider this method for the calculate degree of coupling instead of this one? I feel like this is more reliable compared to this one.
Mm.
And then I also compare the calculation. So we have a few formula. So this two is from the poly books.
Mm.
So basically this also from the poly books, but this one based on the energy.
Mm.
And this one is based on the degree of coupling.
Yeah.
And this one, when we apply metallic damper or any kind of this energy dissipation device. So basically, for example, the degree of coupling 60%. So 60% for coupling beam and 40% for the walls. So 0.4 times the initial damping, 0.05, and then 60% from the coupling beam, and then equivalent damping for the damper is 30%. So this is another way to calculate if the equivalent damping of the system. And then this is
damping is your calculation or
no, this is from the book, Sensei.
from the book?
Yes, from the book. So I just comparing the calculations.
Yeah.
And this also from the poly, but is from based on the energy. And this one is from your formula for from Naki-san. So I compare. So this is formula based on energy, this one. And this one is based on these two. So we can see here. So average energy, this is like 70% and this almost the same. with this one, if you compare. And also, this is for the bigger beam. It's like almost the same. When we use the average and formula,
could you go back? Could you go back? うーん So in this case, only steel beam.
this is only steel beam.
There is
This
no visco sample. Right?
Yes, it's only this one and this one.
Okay. And so. Let's see. Oh, mm. Okay, you have a dumping of wall on the beam so small.
It's a small.
So small.
This one, since I use the formula of from the polybooks. This one,
Mm.
steel frame.
Mm.
This is from Stera 3D data.
Because beam is not yielding, so energy dissipation is very small.
This one is a small beam, sensei. So
small beam.
actually the beam is yielding. This one is the bigger beam, so it's 80%, like 0.
Mm. But the wall dissipates so much energy.
Yes.
Mm.
If I open here, if you check the energy calculation, for example, this one, mostly at the bottom,
Mm.
this is
Mm.
this wall energy. At the bottom, the wall energy is very big and also similar to this one. This the bottom wall energy is a big one. Very big. So and the ratio is small. This
And the ductility factor of the wall is
this
lower part is always yielding. Mm. Mm. How about the case of the paper? I mean, the person of Tokyo Institute of Technology, they also analyzed the coupling wall.
yes, but they but he compare this is his paper, but he's only compare time history analysis and he calculate displacement based design. They have
He
and
examined the equivalent dumping of wall and beam separately.
yes, this one. And this is for the walls, and this is for coupling beam, and then he used this formula.
And how much value of this value in his model?
He doesn't show in here. He just show the calculations. And then he just put the result at the end. He doesn't show properly one by one what he's calculate, but he just put a result based on the initial drift of the building and for displacement.
How much depth of the wall he analyzed? Thickness.
Thickness. Wall element is 400.
Section.
this wall design into the wall. Does it stick? The height is 3.5,
Mhm.
but the thickness he doesn't mention. It's only mentioned the height of the walls, the interstory height.
So I'm curious if he consider damage of the beam, damage of the wall. I mean, in our case, if we push over or analysis, dynamic analysis, wall is yielding also.
Yes.
And I don't know in this case, we consider yielding of the wall.
He doesn't mention. He only compared the result based on the flow displacement and interstory drift. Not he doesn't even compare about the ductility and other.
So this is the only paper, I mean, writing about his study in detail.
Actually, there's one paper. I this author actually have similar procedure with him. This is from Matthew, and I think this is a very famous researcher. So basically, and even this one is almost the same.
Mhm.
The same procedure, and he also compared with the displacement design method calculation, and he compared with the
How about the
temperature
thickness of wall? Is it
thickness of the wall.
explained here?
This is case study of the structure.
Mm.
So flow area, and then this is his nice. This is the copper wall. It doesn't. Okay, this one thickness coupling beam is 200 and height 800, and then coupling beam span thickness of the wall 250 since 250 mm.
Oh, only 250.
And the length of the wall is 4 meter.
Even your model is thicker than this one.
Yes, 500.
So actually, the energy dissipation of this model, we expect energy dissipation of coupling beam, right?
Yes.
By putting damper. But actually, wall also yielding
Yes.
and dissipate energy.
Mm.
So if we put many damper in coupling beam, most of energy dissipation is taken by wall in some case.
Okay. Because
So,
the wall is too thick.
so how to say? And the degree of coupling in elastic range, I mean, and in elastic range, degree of coupling change. For example, in case of steel beam with strong steel beam, as you analyzed, beam is not yielding. So degree of coupling is, I remember 0.8 or something, right? Very large value.
What?
No, 54%.
54%.
This is a case of your pushover,
Yes.
right?
Yes.
So in this case, T is calculated based on max beam. Max beam, right?
Yes.
So beam is not yielding. So in this case, coupling ratio is small.
Mhm.
But if you consider the capacity
Mm.
of the beam,
It's very.
coupling ratio is
Mm.
very large. So,
And Sensei,
Mhm.
for 10-story building, based on this study from the Tokyo Institute,
Mhm.
he said that for lower story building,
Mm.
it's normal to have less than 50. Like in his conclusions here,
Mm.
low to mid rise story couple wall,
Mm.
the degree of coupling is around 25 to 40%. For only like high rise building is around 50% and 60% for degree of
So,
coupling.
is he talking about elastic degree of coupling or inelastic degree of coupling?
He doesn't elastic or inelastic.
Mm.
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 Here,
Could you go back to your Excel file again?
okay.
Why this value is same?
This is taken from the data beam, max beam sensei.
But this one you didn't use max beam.
Yes.
You use data
So
beam.
this one we should take from here.
Hmm?
So should taken from here. This one
No,
for
I'm
the
talking
wall,
about the wall. Moment of wall.
data wall.
You taken from data wall?
This one sensei.
Could you go back to Excel file?
Mhm.
No, my question is this one.
Yes.
This is a moment of shear wall, right?
Yes, moment of shear wall. So moment of shear wall we can take from the data wall.
Data wall, but I couldn't find this value. Yeah.
Data wall only have QY.
Uh-huh. So how did you get MY?
MY I just take from the max wall actually. So I should take from here probably. Is there possible we can take MY from the data wall sensei?
Yeah, I can modify Stella to you can get the MY. Again, I will, the degree of coupling is calculated from a moment
Mm.
of bottom of shear wall and the shear force of coupling beam,
Yes.
right?
Yes.
But it depends on the loading condition.
Yes. But last time, Sensei, we tried to change the pushover, like 1/100 or 1/250. It doesn't much difference.
Yeah, because
Mm.
you calculate, you calculate moment from max wall.
Yeah, maximum.
You calculate using max wall. And 1/100 to 1/50 or
200.
1/250, the coupling ratio doesn't change so much.
Yes, it's only like 1%.
Could you show me the data again? Coupling ratio. Well, you are talking about which one? This one?
Yes.
And so this is how much target displacement?
1/250.
1/250. Do we have a result of another pushover?
This one. So this is 1/200. This is 100. 100.
Mm.
52. 553.
Okay, now it's very important to discuss about how much energy dissipated by coupling wall and how much energy dissipated by coupling beam. So, so it's a kind of a ratio comparison, damage of beam or damage of wall. So in our case, always wall damage go apart and dissipate a lot of energy.
Yes.
We change, damper, they doesn't contribute so much because damage of beam, damage of wall is dominant.
If I
So I know some people studied this one, putting some pin support at the bottom of each wall. And connecting by coupling beam. So in this case, almost zero energy dissipation by wall because moment is zero,
Yes.
right? So it's a very extreme case, but you can control energy dissipation by coupling beam only. You don't need to care about the damage of wall or energy dissipation of wall. But this is a little bit extreme case.
Yes.
So in our case, we must be careful how to deal with
Sensei.
yeah.
But if we like this one is the combination of the damper, we can see that the wall doesn't damage so much because most of energy taken by viscoelastic.
Oh, really?
Yes. Yeah, like wall is almost like 5%. This one also. And this one too. Like less than 5%. If we can check the for example this one. Energy for the wall is not so big.
It's interesting.
For example, this one. It's easy to see.
Do you have the Stella model of this case?
Yes, I do.
Can you run?
Smooth screen. And
You should save all your cases.
and this one is 500.
Yeah, I want to see the dynamic analysis.
Kind of understand.
Oh, nothing.
Okay. Is it okay?
So, so you calculated coupling ratio by pushover, even, I mean, in the case of viscous damper.
Yes.
Mm.
But Sensei,
Mm.
for the viscoelastic damper, I didn't calculate by pushover. I calculate based on the stiffness and the coefficient of damping. There's a formula to calculate energy and the damping for the viscoelastic. It doesn't only metallic is based on the pushover.
Mm. 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 How much coupling ratio, degree of coupling for building with viscoelastic damper?
This one is around 50-70%.
So it doesn't change so much.
And this one 65 and this is
Yeah.
50%.
Mm. Okay. Okay. Mm. 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 Okay. Mm. Mm. So in case you have a steel beam or a metallic damper, you can calculate the degree of coupling by pushover.
Yes.
Pushover. But if in case of viscoelastic damper, you cannot calculate the degree of coupling.
How like but in the question here in the max beam max beam, for example, viscoelastic, for example, this one. In the max beam, there is a Q here. We cannot use this one, Sensei.
Mm.
What is this Q represent for?
Viscoelastic damper include one spring
Mm-hmm.
and parallel to dashpot. Right? This is a model of viscoelastic damper.
Yes.
So in case of static, this dashpot is 0.
Okay.
So only its small stiffness, contribute or resist against the shear force.
Mm-hmm.
So this value is actually very small compared to other cases. I don't know.
Mm-hmm.
5,100. It's not so small. Mm. This result of pushover.
Yes.
But the displacement is 0.
Yes, it's 5.0.
Mm. Mm. ちょっと考えればね。Mm. Do you think you can calculate the degree of coupling from dynamic analysis? So from dynamic analysis, you can get the max wall,
Mm-hmm.
max beam,
Mm-hmm.
right? So you
Yes.
can calculate the degree of coupling similar to pushover.
Yes. I could try that, Sensei. And I can send you the result.
Yeah, so degree of coupling may be one research subject, in my opinion.
I also find a paper, Sensei.
Yeah.
This researcher like study about degree of coupling.
Mhm.
So he limit degree of coupling from 30 until 60, and with different number of story and different period of the building. It also have different response with degree of coupling. For example, this is 0.3 time period, and 0.3 and 0.5 is very low story building. So we can see the degree of coupling is only around 10 to 30, and also here. It doesn't reach, when we see 40 to 50% is very low. So in the for lower story building, degree of coupling is actually around 10% to 30%. When we have higher number story, for example, 15 to 25, so high number of period is much more higher. For example, this is for the high story building. So we can see they have more degree of coupling.
Could you show me the definition of degree of coupling?
Degree
Equation.
of coupling here is this one.
Which one?
This one.
This one. Yeah.
Yes.
So if you want to reduce degree of coupling, what you can do?
We
This part
reduce.
is the same.
Yes. Reduce. If we want to reduce the degree of coupling, we have to reduce the capacity of the beam. So these two different building, with one is a smaller beam and another one is bigger beam but smaller wall. This one is the A one is the bigger, much more stronger wall.
Really? But the wall is also big wall here. So it looks this part sigma MW is different. Because this is very big moment.
Mhm.
And this is small. So degree of coupling actually, suppose if you have both same coupling beam, and so if you want to control degree of coupling, you can um, なんていうのかな。
Reduce the size of the wall.
Yeah. So in our case, degree of coupling is, I remember 80%.
This,
80%,
this is for steel beam,
50%,
50%.
50%.
Yeah.
So
This
it's
is
very,
for, yeah, if you have smaller beam, so it become 27%.
so it means, could you go back to the picture?
Picture.
Yeah. Yeah, this one.
Mm.
So, okay. So suppose this is a strong beam. So it means strong beam. And if we change the same wall but weak beam, then this one change.
Yes, yes, yes.
This one change. Okay. So degree of coupling will be reduced. Yeah, right. Yeah. If we divide EFL sigma m plus 1, right? If we divide top and bottom by same this one,
Mhm.
the equation will be like this.
Yes.
And if we reduce this one, yeah, this value will be getting smaller. Okay. Okay, one idea is to you replace this one to damper and making weak beam,
Mhm.
so you can reduce degree of coupling. Or you can use this weak beam. Okay. Okay. So could you go back to Excel file?
Okay.
So I don't, maybe this is not correct.
Yes.
Maybe you should use this one.
Yes, yes, yes.
And if you use this value, how about system damping?
This one. Maybe I should compare with the dynamic results instead.
Dynamic result of what?
For viscoelastic, the model with viscoelastic. to get the compare the degree of coupling, because
Mm.
in pushover viscoelastic doesn't respond.
Yeah. Mm. Mm. Mhm.
For this one, the equivalent damping of viscoelastic is based on the manual calculation. This is not based on the Stera 3D pushover.
Mm. So the paper you found,
Yes.
they compare different degree of coupling.
Yes. Different number of height, number story,
Mhm.
and the period of the building, degree of coupling, and flexure of restraint.
And how they decide optimum degree of coupling.
This is the conclusions.
They are discussing about the optimum degree of coupling. What is the conclusion?
The conclusion talk about shear amplification factor is lower when the structure is high flexure over strength. And then nonlinear higher mode effect, the shear force are more significant in building whose fundamental period is greater than 1 and tend to remain constant for the period greater than 1.5 seconds. And then shear amplification is more important for Eastern Canada, where earthquakes are categorized as higher frequency content. And lastly, the seismic amplification of seismic shear force decrease with an increase of degree of coupling.
Only last comment related to degree of coupling. Mm. Mm. And there's no discussion about what is optimum degree of coupling.
Only the one from Tokyo University, they talk about number 4 and number 5 and number 6. For mid to lower to mid-rise couple walls is around 25% to 40%. For high-rise building is 50% to 60%.
So how they judge optimum or not? What is the criteria?
This one, approach energy dissipation.
Energy dissipation capacity. So maybe we can draw degree of coupling, horizontal axis, and energy dissipation for system in vertical axis,
Okay.
right? And if input is also degree of coupling may change.
Yes.
You obtained by pushover,
Yes.
but if this degree of coupling changed by earthquake, maybe, for example, epicenter earthquake degree of coupling is this value,
Okay.
and equivalent energy is this value.
Yes.
So you can plot here. And if you another earthquake like this, like this, like this, so you can say energy dissipation is getting larger if you increase degree of coupling.
Okay.
Or opposite. But we don't know. So it's worth to check.
Okay.
Right? Okay, it's something interesting, I think. And this is a case of, for example, metallic damper. And viscoelastic damper may have different relationship.
Okay.
And if you mix together, maybe another curve.
Okay, sense. I will
And
check.
yeah, the final target is if you have a building, you have a target deformation, right?
Yes.
And what you need is capacity spectrum method or displacement based result. What you need is equivalent period and equivalent damping to satisfy target displacement.
Yes.
Okay. So you can control displacement by
Damping.
damping, but the damping is also related to degree of coupling, maybe. So anyway, we want to make some story how
Mhm.
to design the building. Mm. So not only increase the damper
Mhm.
of the coupling beam, but also we must be careful to check degree of coupling. Mm. Okay, let's continue.
Okay,
to, to think about, yeah.
maybe from this study also we can determine the optimized equivalent damping for the damper and the structure.
Mm.
So when structure is when designer want to design damper, they can consider how much percentage they can apply to the building.
Mm. Yeah, yeah. And still, I don't know
Mm.
what is the definition of degree of coupling in case of in this paper, for example.
In this paper?
We know the formula,
Yes.
but is it elastic or nonlinear? If it's nonlinear, moment and shear force change, depends on the nonlinearity.
Mm.
Could you go now?
Then the non-linear, this one, since it,
Yeah.
yeah, go down.
So, could you go? No, it's okay. It's a picture. Could you go up? Could you go up, go up, go up, go up?
This one?
Yeah, this one.
Yeah.
So this moment,
Mm.
we don't know if this is elastic or nonlinear. And also shear force T.
Mhm.
So they use coupling, degree of coupling. They calculate degree of coupling based on these values,
Yes.
right? Well, probably I believe they consider elastic situation.
Okay.
But in
But
real design, you must, consider nonlinear. So these force may change depending on nonlinearity.
what I understand in this paper, Sensei, for the time history analysis is non-linear, but when they calculate the displacement design method, they use for the rotation of the wall, they use plastic. And so, like this, yeah. They use rotation for plastic. So they take the maximum value.
Well, this is a design target. So if we, the target drift of the building, this angle is 1/250, for example. I believe this is pi y w. And they are discussing about the angle of coupling beam. No? It's a geometric relation. Theta c is drift limit taken 2%. Limit state rotation coupling beam. And the yield curvature of the wall section. Yeah, yeah. We obtain rotation of the coupling beam by pushover,
Mhm.
but they don't use pushover, maybe.
Yes.
They use this formula.
Yes.
Okay.
So my question is this formula considered as elastic?
Well, I don't think so. This is
I
no
think
matter, plastic or elastic, no matter.
okay. This is the considered as a maximum rotation.
And I think we saw this equation in the book also.
Yes.
Okay. Mm, mm, my God, I don't have that. Yeah.
It's okay, Sensei.
Mm,
Okay, I will continue my study, Sensei. Thank you so much.
mm. Okay, Sarah-san, you have anything you can show me today?
Yes, I have.
Oh, you came back from Mongo?
Yes.
Oh, okay.
Oh, Sensei, she's already in Mongolia now.
Ah, she's in Mongolia now.
Yeah.
Okay.
Can you
Did
see
you
this?
did you receive my email asking Jabi?
Oh, yes. Yeah,
Something?
I did.
So please submit before you come back to Japan.
Okay,
Okay.
I see.
Mm-hmm.
Now I'm gonna talk about DBDM of viscoelastic and metallic damper and the combination of viscoelastic and the metallic. This is the result of wall thickness is 700 and Coulomb is 800. This is metallic 100%, and this is metallic 20%. This result is not good, but this viscoelastic 100% is 100% result is and this is 400% of viscoelastic.
So I mean, the straight line in the bottom.
Mm-hmm.
This is how to say shear force of the equivalent system at the target displacement.
Yeah.
And if it's close to orange curve with capacity curve, so this design is successful. Is that correct?
Okay. And this is a combination of viscoelastic 100 and the metallic 20%.
So in this case, blue line is over the orange curve. So,
and for about viscoelastic 400 and metallic 20%.
It looks
this is yes. And also I also checked the viscoelastic 400 and metallic
うん。
30%.
うん。
This is also good.
うん。うん。
And also in this slide shows the difference of the storage of the each variation
うん。
designs
うん。
for about viscoelastic 100 and this is under Kobe and viscoelastic 100 and viscoelastic 100 combination viscoelastic 100 metallic 20 percent is not good.
うん。Could you go back slide? Could you go back?
I see.
No, not. Could you go back? Go back. One more. Okay, this one. So this is VE 100 M 20%. Okay, could you go to the last slide you showed me? 100 to 20. So 120 is which one?
It's the yellow color ones.
Yellow one.
Yellow one.
Yellow one.
So yellow one is too large deformation.
Yes.
Okay. Yeah, because estimation by equivalent linear, blue line is much larger. Maybe this is the reason. Okay, okay. Yeah, it looks good. Okay. But the yellow color, あ、そっか、イエローカラー。Okay. うん。So only M20K is orange one.
Orange one.
But if you add the viscoelastic, suddenly,
This one.
yeah. Oh, it's also much big difference in blue line and the orange line. なんでだろうな。
I think the combination, the best combination is viscoelastic 400 metallic 30% is this one, I think.
Can you try open metallic 100%? Metallic 100%.
Metallic 100%.
Yes.
This one.
The best scenario is, blue line and orange line are matching quite well at the end of the line. So for example, could you go to next slide? Oh, it's not good. Well, it looks good. Also, it looks good. So VE 400 looks good. And also this one good. This one good. So VE 400 looks good. And could you go down? Final, yeah. So if straight line and the orange line match together, it also gives good result for dynamic analysis. I mean, close to target displacement.
Yeah.
Is that true? Maybe.
Yeah.
V400 looks good, right? In all cases.
Yeah.
Yeah, maybe. Mm,
The light orange and dark blue and green one is good.
mm,
Are good.
mm, mm, mm. 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 Okay. Okay. Mm. Mm. So our target is to use not this one. This is a result of time history analysis, and it
Yeah.
takes time to get this result. And so without using this result, we want to design the building by previous, picture. Could you go?
Mm.
So this is a displacement-based, not this one. Could you go on? This is a displacement-based design. So we design the building so that the equivalent linear blue line and the capacity curve match together. So we believe
Yeah.
this is the optimum design. Yeah. But yeah, it looks good, but still we must check.
Maybe there's some miscalculation in the metallic displacement based design. I will double check, Sensei.
Okay. Okay. サラさん also please think about the story of your graduation thesis. You must submit it in December. So we still have 2 or 3 months, but and also you can do something more.
Okay, I see.
Sensei, can she proceed to 20 story? So she can compare the result between 10 story, 15 story, and
Yeah.
20 story.
Yeah, okay. Of course. But
Do you have any idea to add on, Sensei?
なんていうのかな。I want to make the story how to design coupling wall.
Okay.
So degree of coupling is one, なんていうのかな。design parameter. And also the accuracy of displacement-based design. It's not completed yet. And also how to calculate damping coefficient.
Okay.
There are many uncompleted items. Yeah, we can proceed many buildings, but I want to solve the problem one by one. Otherwise, if we continue many models, and once we have a mistake or once we change idea, you must repeat everything from the beginning.
Right.
We must make some story how to design coupling wall. And even we don't know what is the definition of degree of coupling. They are using elastic force, or how about in case of nonlinear?
Okay.
So we don't know still.
Okay.
And we use energy formula to calculate system damping, combining equivalent damping of wall and equivalent damping of coupling beam. We combine together by using energy formula. But the Priestley proposed simple formula using the degree of coupling ratio, right?
Yes.
We must find out which one is better, or yeah, it's not completed yet. Yeah, but yeah, in the same time, of course, if we want to check effect of number of story, maybe Sarah-san can conduct some, well, case study. Okay, so let's think about
Okay, Sensei.
and continue
Okay,
to
sensei.
check what. So I want to make everything clear.
Right.
Okay, I see.
Okay, so next, Saraya-san, do you have anything? Show me.
Since actually for the past few days I was in Hiroshima and Osaka, so I do not have anything new to show.
Did you go to Hiroshima or you will go?
Yes, Sensei, I already went.
How about Hiroshima?
Sensei, it was very nice, as with all the memorials of Japan. It was very descriptive of the different sufferings that happened due to the atom bomb.
How was the weather?
Weather was, it was humid, but the sun was not out, so it was little bit better.
You are lucky. Yeah.
Yes.
Did you go to Miyajima also?
Yes, we went to Miyajima also. And we also went to Himeji Castle on our way back.
Okay. Himeji Castle is so beautiful.
Yes, yes.
Yeah. Okay. Good. じゃあ、Okay, shall we decide next meeting?
先
生。
はいはい。
いいですか？
はいはい。
画面共有して。
はいはい。ちょっと待って。はい。ちょっと待って。いいか。今。はい。
今日の同化スゼミの振動体実験のことなんですけど、今日見てたのは構造互角論文集で、あと公害とかを調べていくと、実装の実験は、試験体の図がこの右のような形で、実装で、変異は36実装計測、加速度前走計測で、入力はここ自波で時間刻み4分の1倍で入力していて、試験体は、板バネは1から3層目が厚さ5ミリ、4から6が厚さ4.5ミリ、7から10が厚さ4ミリで、この平板のところに4つ、柱をつけていて、入力方向は Y 軸方向に入力してます。
入力方向は Y 軸方向だけってことね。
はい、一軸過信です。
そっかそっか。要するに板の、曲げられる方向ってことかな。
はい、逆軸の方向だけ。
逆軸の方向ね。
で、試験体の総重量が、43.6 キロニュートンで、これを11で割ると各層大体404キログラム。柱はヤングケースが書いてなか何を使ったとは書いてなかったんですけど、ヤングケースがこの 2.05 って書いてたので、おそらく一般鋼材を使っていると思います。で、一般鋼材の、単位密度が 7.85 で、これに床の重さの体積をかけると 392kg になったので、大体、計算上、各層約404で、392なんで、これに柱を合わせれば、計算通り。
じゃあ、重りを特につけてるわけじゃないんだ。
はい、本当に床の重さだけで。
床の重さってことね。そういうふうにしてるのかな。重たくしてる、
そうですね。で、実験を行ったかなと思います。で、一次固有周期が 0.93Hz で 1.75 秒、一次元数 1.1%、二次 2.4% で実験を行っていたようです。で、安藤狭間の、振動台の規格を見ると、正確35トンフォースって書いてたので、最大積載能力が300キロぐらい、300キロニュートンぐらいだと思うので、これと同じようなものを作るんだったら全然 問題なく乗ると。
全然楽勝だね。
はい。これよりも大きいものでも
うん。
問題はないと思いますね。
うん。
なんで、その、対象とする自治体を考えるんだったら、JSSI に載っているトリムモデルの
うん
10層をそのまま10失点に変換するか、20層、20層分にしてもいいのかなって思ったりしてます。
20層
20層そのまま20層でも、
それと高さ何メーターぐらいな
高さは計算しないといけないですけど、
今言ってるのは同じような
はい、
床と板バネで、
はい、20層分。
うーん、
この床材を組み立てるときに、一つが重すぎると大変なので、
うん、
それだったら分けてる方が組み立てやすいのかなと思ったり。
ユニットで分けて積み重ねるってこと
はい、はい、
うん。まあそうだけど、ただ下の方はどんどんザク体力も計算しておかないとね。
そうですね。
うん。
この実験は柱も鋼材を使ってるみたいなんですけど、鋼材だと蘇生してないのかなっていうのがちょっと疑問なんですけど、この実験で。
うん、でも蘇生させるわけいかないよね、きっとね。
はい、繰り返し入力してるので、
うん。
なんで板バネとは言ってるんですけど、
うん。
もうちょっと違う材料、もっと男性系のやつ使った方がいいかなって思います。
うん。う
でも
ん。
これを参考にすれば、この実験で非精神の実験をしていなくて、全部ダンパーつけてるモデルしか実験してないんで、
うん。
どんだけ入れてるか、非精神どんだけ入れるかは分かんないんですけど、
えっと、精神で、例えば相関変形がこれぐらい揺れてるっていうのは分かってるね。
相関は出てます。相関じゃなくて、ダンパー付きは。ただ、非精神が出てないです。
うん。でも、ダンパー付きの相関変形で、これ、上下固定の板バネがね、ある変形角で変形してるときにこうするかどうかって分かるんだね。
最大相対変異は6ミリです。
6ミリ。ああ。
11回で。
280で6ミリ。
いや、違います。3908で6ミリです。
最上階が6ミリ
はい。
本当で全然500分の1か600分の1ぐらいってことか。
図10に見えますか？図の10に。
うん。
相対変異が真ん中の図なんですけど、
うん。
HHH の
相対
これがダンパーのなんですか、HH だったら全部履歴で。
うん、うん、うん。これ、相対変異に、
相関とは書いてなくて、相対って書いてあるんで、
そう、じゃあ、振動台の変異を、振動台からの相対変異っていう
はい。
ことね。
多分そうだと思います。
うーん。
で、絶対加速度が
うん。
40カルぐらい。
うーん。だから絶対あれだよ、蘇生化させないような揺
小さい変異。
れにしてんだな。
はい。
で、ダンパーは粘性系。
HHH が履歴、年生とかの組み合わせを書いてます。
で、履歴は相当小さい変形でこうするような履歴系なんだよね、きっとね。我々の場合にどれくらい変形させるかを想定しないと、これ同じ試験体だとほとんど、
変形させれないですね。
変形させれないかもしれないね。
はい。
うん。うん。うん。うん。あとは完全に床が5だから、曲げ、こうかん、なんていうモデルは先端変形だけってことだね。先端多視点形だよね。
はい。
うん まあでも工事モードのチェックはできるか。
はい。なんか曲げが入るとちょっとどうかした、ちゃんと動くのか心配で、
うん、
先代だけの方がいいかなって思うんですけど。
そうだね。うん。わかった。じゃあこれすごい参考になるね。
はい。
うん。じゃあこれでちょっと明日議論してみようか。
明日これ、何を説明すればいいですか？実験のことについては。
今の資料をちょっと見せて、
はい。
基本設計はうちの大学でやると。
はい。
それで、材料も加工もうちでやると。だから、振動台を、どこの会社の振動台で、どの期間抑えてもらうかを、明日相談しようかな。うん、もうそういう話にしちゃっていいかな。
なんか6社が本当にやることを把握しているのかどうかがちょっと。
もうやるってこっちが言わないと多分、あんまりやる気がちょっと感じられないっていうかさ、天井実験のまとめで、なんか、話が進んでるので、はっきり言うとね、自動走行にしてたから、あんまり彼らは、ものじゃないしって感じで、ちょっとこう、力が入ってなかったと思うんだよね。
はい。
だから今回、今のモデルのいいところは、自動走行っぽくないじゃん。まあ一応、高層建物の縮小って感じでしょ？
のはずです。論文には詳しくは書いてなくて、なんか対象は何とは。
で、それでいいと思うな。だから俺最初自動走行を試験体にしようかなってさ、
はい。
まあ、今でも半分は思ってんだけど、
僕も思ってます。そっちの方が早いかなっていう。
そうそうそう。既製品もあるしね、
はい。
なんか過去に実験した試験体も残ってそうだから、
はい。
ただ、研究元としては、自動走行に限定しない方が
そうですね。
いいね、きっとね。
はい。
で、明日ちょっとその辺を、だから今の資料、ちょっとぜひ見せて。
はい。わかりました。
で、うちの大学がどんどん決めて、やりましょう。やりたいことをやらせてもらおう。
はい。
はい。
わかりました。
Okay, so shall we discuss next meeting? Today is 5. So next week we must go to Kyoto for AIJ meeting. So maybe after we come back. そうか、そっちのモニタリング。20 or 21 afternoon. Which one do you prefer?
I'm fine with both, Sensei.
Both okay.
Yeah.
In case of 20, I can do from 3 o'clock afternoon. Or 21 from maybe 1 o'clock. Okay, 21,
21.
1 o'clock.
Okay, Sensei.
Okay. Okay, shall we finish? Does everyone attend the farewell meeting, farewell party?
I will join, Sensei.
Yes, Sensei.
Okay, good, good. So let's enjoy. Okay, bye bye.
Bye bye.